This is an explanation of AVL trees. AVL trees are binary search trees where we control the depth of the tree so it doesn't get too big. Okay, so what we define as a height balance tree is a tree where the depth of the left side and the depth of the right side differ by at most 1. Okay, and also we want the left subtree and the right subtree to be height balanced themselves. Okay, so so what do we have here as examples? Here is a tree of depth 1. Here is a tree of depth 2, and the two subtrees here of depth of height 1 and here of height 0 differ by at most 1. So here we have 1, 1, 2, and here we have 1, 2, 1, and 3. So there's a difference, but only of 1. And here we have 1, 1, 2, 3, and here we have 1, 2, and that 4. So it's still, the differences are only 1. But here, if we go and add this one node, so now we have 1, 2, 3, then at this moment we don't have a height balance tree, right? Because on the right hand side we have a tree of depth 2 and here of height 2, and here we have of height 0. So there's a gap of 2, and that is too much. Okay. So an AVL tree is simply a height balanced binary search tree, and so that means that we put the keys into this tree in the regular order, where to the left side you go to a smaller elements and to the right side you go to upper elements, but we also are going to keep it height balanced. Okay, and that would make it possible for us to do fetch, insert, delete, split, and join all in log n time. Okay, so to implement this, what we do is for each node we have a variable that measures the difference between the heights of the left and right subtrees. Okay, so let's see what this is here. So first let's see what are the depths. So this is 1, 1, 1, 1. This is 2. This is 2. This is 3. This is 4. Okay, and the difference between the left and the right is here. It's 0, 0, 0, 0. Here it's also 0. Here left minus right is -1. Here dog left minus right is -1. And here it is left is 3, right is 2, that's 1. So so that's the numbers that we have here. Of course, these numbers have to be 0, 1, or -1, otherwise the tree is not height balanced. Okay, so to insert data, we just insert it in the usual way as in the binary search tree. Let's say if we want to insert ant, then we go here, ant, before we were smaller than ant, smaller than cat, so we add ant here, and we connect it to this node, and we recalculate the balance variables. Okay, so let's see a case that this is done. So suppose we're inserting hen, and so in this case we go down this path and we add hen here. Okay, so now that we have hen here, the depths are 0, 1, 2, and so the difference right here is 2. Is left minus right is actually -2, and so this is not a good situation. We don't allow that. So what we're going to do is we're going to rotate on this edge. Okay, so we do rotate left. Okay, and that gives us this new configuration here where the tree is height balanced. Okay, so we basically made hen go a little bit higher up the tree, one up the tree, so that the path to it next time that we search for it is not so long. So in general, we need 1 or 2 rotations to get an unbalanced tree that has been just after 1 insertions into balance again. Okay, so let's look at 2 cases. So here we have balanced tree, and suppose that we're adding the node 18. Okay, so now we have a correct binary search tree, but it's not balanced. But we can easily balance it by right rotating this node. So that would give us, instead of this, it would give us 19 going to 23 and going to 18. Okay, so this case requires 1 rotation. Here is a slightly harder case where we need 2 rotations. So suppose we're adding the node 20, and now we need 1 left rotation first to get the 20 up. So left rotate this node, so we get 23 going to 20 going to 19, and now we do right rotate of this node, and what we get is 20 that goes here to 19, and that goes here to 23. So here we needed 2 rotations, and again this 20 node will come instead of this. Here we'll have the 20 and the 2 edges coming out of it. Okay, so in general we can think about it in the following way. Suppose we have a balanced tree where each one of these subtrees is balanced, and we have 4 ways in order to make the tree unbalanced when we add a single node. So we can make this one unbalanced, we can make this one unbalanced, this one unbalanced, this one unbalanced, and we call these cases going left and left, we call this left left, this we call left right, this we call right left, and this we call right right. And for each one of these cases we need 1 or 2 rotations in order to fix it and make the new tree balanced again. So that's summarized in this table here. If we have the left right case, then we need to do one left rotation to get it to here, and then another right rotation to get it here. If we have a left case like this, then we just need 1 rotation. So that's pretty much the whole algorithm. You go up the tree and fix the unbalanced subtrees so they're all balanced.